we're going to start with our old familiar lines here. And the goal of this demo is just to kind of give you a little more intuition about what you're doing when you're taking a Fourier transform and what it means to reconstruct a signal. So we're going to start by defining a signal of length 512. Not too big of a number, not too small of a number. It's going to give us a signal that we can look at and not be too disgusted. So here's n, our time series. And we're going to define a sampling rate. I'm picking this pretty arbitrarily. We're going to call it 800. And I'm defining a signal. I picked this signal because it's easy to look at. It's really just an arbitrary signal. 0.05. So if you're wondering why I'm doing all this crazy crap, it's just because it's more complicated than a sine wave, and it's easy to look at. Times n dot. And I'm going to post this code online. Okay, so just to look at this guy, maybe, there it is.
That's nice.
So it's not too painful to look at. That's really my only goal with that. And I want to do some other things to that signal. Let's look at it down here, such as make it stretch in time or something like that. And I can do that by changing these two coefficients. But the way I'm going to handle this is just toss in an extra parameter that lets me tweak these things easily. So if I make F1, nothing's changed. If I make F2, guess what? We're going to get higher frequency content. Stuff.m. So I run this again, and it doesn't read.
You have to plot it.
Oh, God, it's my first day. So it's a little higher frequency now. If I want to lower that, no, it's lower frequency. But in general, we're just going to stick with this and leave it for now. And the first thing that we're going to do to this signal is take our Fourier transform. And we're going to start by making some k's. This is where k equals also 0 to n minus 1. And omega equals big K over n times 2 minus 1.
You got a little function.
Yeah, it's nice. So, Chet, why did you pick this crazy thing for omega? Doesn't exist yet. I picked it because it goes from, -1 to 1 and contains 512 points. So all I'm really doing here is I have a number, now I'm scaling it, then I'm multiplying it by 2, so this goes from 0 to 2, subtracting 1, goes from -1 to 1. And then those are going to be the frequencies that I plot against my FFT. And you'll see that in a second. All we really need to do to get that data is do FFT of x. We're going to call that big X. And I'll talk about zero padding in a second. Zero padding is actually super easy using the FFT command. So let's run this. And then we're going to plot the absolute value of the FFT of x. Actually, we can just plot x. And that's going to look like this guy here, where our axis is in samples, which isn't the most convenient thing to look at. We need to put in a request to get a larger monitor here. This thing is beyond silly.
Wait, our axis is in bins.
It's in bins, sorry.
Yeah.
But it's in a unit that's really not that illuminating.
Yeah.
So what we're going to do now is, instead of plotting it like that, we're going to plot it against omega. So it goes from -1 to 1. And you know that your -1 corresponds to a frequency of -pi. +1 corresponds to a frequency of pi.
That's the MATLAB convention.
Any problems so far?
Yeah, so I remember, like, on the homeworks and the other DFTs we've been doing, they've been arranged differently so that we have the positive frequencies first and then the negative frequencies.
Yeah, let's make that happen.
Cool.
So let's bring this into the code. Actually, I want to I'm going to copy this code because it'll save me the time of writing it, and we'll analyze it now. So the first, that wasn't very much code at all. The first code was just what we just did, except I want it in red. So radian frequencies down here, magnitude, and this is a spectrum. If you just add the word FFT shift, it takes your negative frequencies and puts them where you would expect negative frequencies to be. So I will note that on this plot, the omega axis is not correctly labeled. And looking at it again, we'll discuss why. Because your zero frequency is down here and up here, where it says -1, +1. To correctly label it using that axis, you pop in the FFT shift. So this bit here used to be over here, and this bit here used to be down here. Now it's a spectrum like you would expect, and it's symmetrical, and it's always going to be symmetrical because you're going to be working with real signals. Real signal equals symmetrical spectrum, which is something that we'll touch on later. So you don't have to understand the reason, just know that as long as you're working with audio data that is real, your spectrum will be symmetrical, which is why it's safe to only look at the positive frequencies, as you will so often do. Okay, so the question came up about zero padding. If you want to zero pad, all you really need to do is pass in not just your signal, but an n, so some larger n, so 1024 maybe. That looks beautiful. So when your thingy looks like this, it's because it's trying to plot a complex number. So it plots it in on the z-plane, and you get this thing that goes around and around and around. It looks like junk, and you shouldn't spend too much time thinking about it. It means you left out your abs. Never forget your abs. Never skip abs day. I almost said it. So here you are. You've got seemingly better frequency resolution here. You could have obtained the same result by doing spectral interpolation. Not something you have to worry about heavily right now, but I mean, you can zero pad this thing till the cows come home. We use powers of 2 conventionally because the FFT is fast with powers of 2 for reasons that you don't have to worry about, but you can bug me later if you want to know more about that. So you're increasing the number of bins in your FFT, and you're getting the same information.
What is it doing if it's not zero padding? I'm doing like Cooley 2D.
It is doing whatever size you have.
So it's just doing DFT. Then when you put in the FFT function, the padding is specific size for zero padding.
Say that again?
So when you,
It uses whatever size the array is if you don't give it a size.
gotcha.
It's still going to do an FFT to my knowledge. I don't think it breaks down and does an n squared DFT.
It'll choose the optimum algorithm, so it'll analyze the size. And if you give it a prime number of samples, it'll do just a plain DFT.
Oh, okay.
But if it's a composite number, it's got a sequence of fast alternatives, and if it's a power of 2, it'll do the FFT that we're normally going to use.
It goes to n squared with prime.
Where does n squared come up?
The runtime.
Oh, yeah, for a prime number, it's n squared, right? 'Cause
That's
you
a
have
fun
n
fact.
operations for each bin, and there's n bins.
Okay.
Has this always been the same signal, what we're seeing?
Yes. The difference in time domain is that you're taking it and just appending a bunch of zeros to the end. So if you tell it 1024 and it's a 512 signal, the last 512 samples are going to be all 0. Okay, cool.
Can you
So
say why they will be all 0 again?
because you're zero padding.
So, wait, so what does that really do?
It gives you better frequency resolution. So when you have a longer signal, you have more bins. So maybe you didn't have a bin for, if you're doing a 512 point DFT and you want to know what the energy is at 2 hertz, it's not a trivially easy thing to figure that out. You can figure it out even with 512, but you have to do some DSP tricks, interpolation, namely.
So 0 padding is interpolation, basically?
Right.
Zero padding in the time domain is interpolation in the frequency domain.
And why is it called 0 padding? What exactly are we doing with zeros?
You are marker. This is why I wanted the eraser. You have your signal, maybe your signal was 1, 2, 3, 4. Once you've zero padded it, you're just sticking zeros on the end. Cool?
Wait, so that's your FFT signal?
That's the time domain signal that you're passing into your FFT. So the zero padding happens prior to any DFT stuff.
Oh, I see.
So why does it have the effect it has?
Because you have more time samples, and just because you have more time samples, you have more bins.
So more resolution.
And because you have more bins, the number of frequencies that fall into each bin is smaller.
So why do it like, doesn't this seem like a bit of a contrived method? Why can't you just pass in like how many bins you want it to have? Like I want it to have like a million bins, or is that what we're doing?
That is what you're doing, essentially.
Oh, so like zero padding it literally like this, and just telling MATLAB like do it with n equals, what did you do, 1024 times 8? That's the same thing basically.
Yeah, that's what,
Mhm.
that's it.
So if you're just joining us, FFT and DFT will often be used interchangeably. As far as most of you care, they're the same thing. FFT is a different algorithm that gives you the same result as the DFT, much faster.
And how does FFT work differently?
What?
How does FFT work differently? Because we studied the DFT and computed the dot product. I mean this big matrix multiplication of S sub k times.
So the FFT is a recursive algorithm, and it takes advantages of symmetries in the DFT formula, and it continuously breaks things into chunks of 2, which is the reason that it's optimized for powers of 2. And every time it does that, it saves a bit of work, and so it can break it down into a factor of 2, log base 2 of n times. Yes, and it takes n time to do each of those computations. So you get n log n time for an FFT, whereas it takes n squared time to do a DFT. And that's because you have the 2 sums. You're looping over n, and then you're looping over k. That was hand wavy.
And if
Have a
you wanna
nice...
see- If you want to see the computational structure, do a Google search, images search for split radix butterfly.
Say again?
Split radix, RADIX butterfly. That's the state-of-the-art FFT algorithm, which we're not covering, but if you're interested, it's pretty. It makes a nice t-shirt.
Makes a nice t-shirt. So I'm going to get... Yes?
when we do the zero padding, we're increasing the bins, but like the data we have is still the same, right?
The data you have is the same. So
How would that like increase it? Like it's like artificially increasing. Right?
it is kind of artificially increasing it. You can get that same information without the zero padding, but you might find it to be a little more difficult. Are you going to cover spectral interpolation at some
It's going
point?
to be among the Fourier theorems. The Fourier theorems will give you the math for exactly why zero padding is ideal spectral interpolation. And I will also be careful not to call it increased resolution, because to increase the resolution in spectrum analysis of sinusoids, you really need more periods of the sinusoids. Here we're only adding zeros, we're adding no new information. So we're adding a lot of bins, and from a graphics raster point of view, we have increased resolution in the spectrum, but that's not the same thing as frequency resolving power, so it's really important not to confuse those terms. So I don't even use the word resolution when I talk about zero padding. I only talk about interpolation. More bins, denser bins, more points around the unit circle. For the same information, exactly the same information, we're just adding zeros.
Okay. Any other questions before we move on?
If we, for example, had more periods, like if we did a zero padded FFT on one period of a known frequency versus doing an FFT of the same length as the one period zero padded, but like let's say we had 8 periods,
You're going to
would
get a
that be
scaled version.
that would be reflected in the bins being, I don't know, 4 or 8 times some sort of proportion of the period, like extra periods amount. Bigger.
So if you have that versus the zero padded version, they're just going to be a constant scalar offset of each other.
Just trying to think of it from like the argument of resolution versus just interpolation.
Well, what I just said doesn't have to be completely obvious to you.
Okay.
So,
Well, let me take a crack.
yeah, go for it.
Take an FFT of one period, you will, and then whether you zero pad or not, well, let's say it was just an FFT of one period. And what you see is a bin at omega 1, k equals 1, you get a number, capital N probably, and then you get 0 everywhere else, all the other bins, because that sine wave had one period under the FFT, so that's the frequency omega 1. And so you only get a single bin of energy there. Well, you get a at 1 and minus 1, where minus 1 is also n minus 1. So you get an impulse at k equals 1 and k equals n minus 1. Now let's say you stretch it to 8 periods. That's k equals 3, I believe. So because, well, no, it's 8 periods, so I guess it's k equals 8, because you have 1, 2, 3, yeah, it's all integers, so yeah, k equals 8. So basically you just move that impulse to k equals 8 instead of k equals 1, so you've got 7 zeros below it. Those are all the interpolation points. Now if you just keep one period and extend with zeros out to 8 times, you'll get a peak at k equals 1, and you'll have 8 samples of, main lobe coming down to 0.
So having the extra periods makes it easier to discriminate what pitch was the actual one present.
Right. Zero padding makes it easier to interpolate the peak, and more periods makes it easier to tell peaks apart. If the peaks are almost on top of each other, no matter how much interpolation you do, they're still on top of each other. To really pull them apart, you want more resolution, which means you need more periods of the signal. That's the only thing that's going to help you pull them apart, see them as separate. Keep them from blending into each other. They melt together if they're not resolved.
Okay. Thanks.
Can I get some thumbs up? I got a couple. I'd like some more. I think if you were confused, you would be asking a question. I hope if you were confused, you'd be asking a question. So
Chet,
we're going to
could
move
you
on.
just tell
Thank
us
you.
what the original signal was? Was it adding two sinusoids? I saw-
Oh, I think it's taking 2 sweeps that go. It's just adding 2 sweeps together that are at different frequencies.
Okay.
It's nothing. You could make this random noise. It would just make this picture harder to look at. This demo works when x equals anything.
So the first picture is the time domain and the second is the FFT. Right?
Exactly. So I am arguing that nothing that I did while Julius was talking was extremely interesting. I added this plot for the time domain signal, and I bounded the axis from 0 to n in x direction and negative to positive 2.5 in y. And I plotted them on subplots. Now I'm going to get rid of this. It's not, correct if I'm using this labeling, and really it's kind of redundant to hold on to all this code. So I'm going to get rid of this, and hopefully no one will miss it. All you need to know is that if you take out the FFT shift, it splits this back up into its original form.
I had one question. What was the point of defining omega that way instead of linspace from -1 to 1 of endpoints?
I could have done that. I just don't use linspace as often as I should.
Okay.
I don't have a better reason than
All
that.
right, all right.
Okay, so we've got this guy here, and as we decided, let's not make this dotty yet. Wow, beautiful. As we decided earlier, if we change F, we can make this look different. We can add more high frequencies, add more low frequencies. So here's your question. If I split F in half, the easy part of the question is what happens to this. The harder part is what happens to this. So start with the easy part.
You have less periods, or
You'll have less periods because generally the frequency is dropping, right?
yeah, and same number of samples, so we just have like it just be like stretched out.
Mm-hmm.
Would it be stretched out?
Yeah. If we plotted 1,000 samples, it would have been the same.
It's stretched on the time domain.
It's stretched in the time domain.
Yeah,
Sorry.
That's what I mean.
Sorry, I guess I spoiled the surprise.
No, I didn't even see what happened to that. Let's see. You can do it again.
Yeah, just say to tell us to look first at the time domain. That was the easy part. And that's what happened.
True. So if you cut the frequencies down, if you stretch it out in the time domain, what happens in frequency domain?
It's compacted.
It gets compact. There's your inverse relationship again. As one gets bigger, the other gets smaller. So what happens when we double the frequency here? What happens if we do it again?
Even more.
So we're about to start doing what?
We're about to start hitting Nyquist.
Yep. What have we done?
Alias.
Aliasing. Good job, team.
And how can you illustrate aliasing in the FFT graph?
Well, you can see like the
I can tell you that it
edges
happened.
there. On the edges there.
And the way that I know it happened is because like right here it drops down to 0. And usually you look at FFT on a log plot because these things that are, looking like 0 aren't as 0 as they could be. That was hand wavy. And you can see the things that are non-zero kind of getting close to the edge. And they've gone off the side.
Is that why those edges are looking all messed up there with that little dip in?
Yeah,
It's the negative frequencies coming back.
coming back, and they cancel out in a way that happens to look like that. And I mean, if you go in and look at your time domain signal, you can see, it's alternating pretty fast. There's also some low frequency content, so not every sample is switching up, down, up, down, up, down. That would be if it was just a pure thing at half the sampling rate. But you've got stuff all over the spectrum. So let's run this again. And go back to our base signal. So now we're going to write some code that lets us reconstruct our signal. So why don't we put that here, and we're going to say that the magnitude, let's do it in a for loop. I think about the best way to start this. We are going to start with a single k value. Let's start with the k value 27. It's a number. That's how I picked it. And we're going to look at the x sub 27. X sub this k, generically, is the variable that we're looking at. So we're taking the frequency bin, number 27, and playing with that. When you do your DFTs, the x sub k's pop out. We're taking the 27th one. So what's the magnitude of this thing equal to? The magnitude of your x sub 27, how do we calculate that? You guys forgot abs day?
Oh, no, yeah, of course. Is doing abs enough? I mean, isn't it, I
Yes.
guess I forget about abs. It like works it out to get the magnitude for complex numbers.
Mm-hmm.
Okay, cool.
So how do we get the phase?
To angle x in this case.
Maybe like the real versus imaginary.
Angle will take care of it for you. Yes, good. It was going to yell at me about that eventually, and I would have stared at it and saying it looks right. I did that a lot when I was making this. So we're going to figure out the contribution from each component. In that case, we want the sine wave that corresponds to this k. So we're going to call this component contribution. And it's a long name, yeah. And it's a clear name, too. We're going to do this, which may not be quite what you're expecting, but I have a reason for doing this, and we'll talk about this line of code in a second. Pi times this k minus 1 over n. I'll even leave some comments in the code for you. Phase over n. So a lot of stuff happened there, and I even got the parentheses right. So let's talk about what happened here. So this is a thing that I did.
I guess that's your frequency, right?
That's your frequency, yeah. But why minus 1?
Oh, shit,
It comes from 0.
Because we kind of from 0.
You're counting from 0. It's MATLAB's indexing. So your array of this k or whatever is going to start from 1, the first index of x. But the first index of x is frequency 0. That's why we subtract 1. So this k minus 1. The reason that we do that, the first frequency is at index 1.
Just because you want the 27th bin, and the 27th bin is index 26.
It's the 27th bin is frequency 26.
Yes. Now, if you want the 27th bin, like, including 0,